in our previous lectures we were discussing about reversible work, irreversibility and exergy, these three important concepts, and now we will solve some problems which will illustrate the use of these concepts. So, we start with problem 8.1. A refrigerator has a freezer at Tf and cold space at Tc, from which energy is removed and rejected to the ambient at Ta as shown in the figure. Assuming that the rate of heat transfer from the cold space Q dot C is same as that from the freezer Q dot F, find an expression for minimum power into the heat pump, I mean which is in this case is a refrigerator, not a heat pump, but conceptually they work in the same way. You have to find out what is the minimum power input. So, minimum power refers to a condition when the minimum power input refers to a condition when the irreversibilities are minimum, and that means it is a reversible refrigerator. So, that is the concept that you have to understand. Maximum power output will correspond to a energy producing device for a reversible heat engine. Energy absorbing device will require minimum power input to run the device for a reversible heat pump or a refrigerator. So, this when it is maximum and minimum you have to understand carefully. When it is energy producing, that energy is maximum because of minimum losses, and when it is energy absorbing, that energy required is minimum to run the show. So, let me make a schematic of this problem. So, you have Q dot C with a temperature Tc, W dot Q dot A, Q dot F. So, this is a cyclic device which is a refrigerator in this case, and it is most important is it is reversible. Okay. So, what are the basic equations that you need to apply for a reversible refrigerator in this case? One is cyclic integral of heat equal to cyclic integral of work, which is the first law. So, let us apply the fundamental laws. Cyclic integral of heat equal to cyclic integral of work. So, cyclic integral of heat for this device. So, we will just write in terms of the rate. So, cyclic integral of the rate of heat transfer is same as cyclic integral of the rate of work done. So, rate of heat transfer is Q dot C plus Q dot F minus Q dot A, right. This is cyclic integral of heat. Cyclic integral of work is minus W dot as per this figure. Second law does not see, first law concerns about work, second law concerns about only heat transfer, because work is a high grade energy, it does not participate in entropy transport. So, second law, you have cyclic integral of del Q over T is equal to 0 for a reversible cycle, right. So, this is Q dot C divided by Tc plus Q dot F divided by Tf minus q dot A by T A is equal to 0. Look carefully that we have taken the temperatures not of the system boundaries here, but the reservoirs here. In this way we have accounted for both internal and external part of the process, whatever is internal plus whatever is external, and ensured that it is both internally and externally reversible. Okay. So, now it is a matter of, so what is given in the problem, let us see. It is given what is q dot F and q dot C, but q dot A is not given. So, let us eliminate q dot A. So, q dot A, from here you can write q dot C into T A by T C plus q dot F into T A by T F. So, then from this equation minus W dot is equal to q dot C into 1 minus T A by T C plus q dot F into 1 minus T A by T F. This is the final expression. So, in this expression you can substitute q dot C is 3 kilowatt, T A, T F, T C all are given. You have to convert those into Kelvin and just substitute, and this will be 0.504 kilowatt for this. See, solving a problem is not about getting the final answer. There is also an insight that needs to be developed. So, let us try to develop an insight of this expression. If you recall that here there is a system to which you have two heat transfers effectively done, and you are trying to find out an expression for the reversible work. So, you can clearly see that this is exergy associated with the heat transfer q dot C, this is exergy associated with the heat transfer q dot F. So, this essentially is an expression that gives the reversible work through exergy balance. Because it is a reversible system, the entire exergy that is supplied is equivalent to the reversible work, there is no irreversibility. Okay. So, you can see that the same problem can be perceived from exergy balance and also directly from a consequence of the first law and the second law. Let us go to the next problem. Let me erase this. A steam turbine receives steam at 6 MPa 800 degree centigrade and it has a heat loss of 49.7 kilojoule per kg and isentropic efficiency of 90%. I have not yet introduced what is isentropic efficiency. So, I will do that in context of this problem and then we will discuss further. For an exit pressure of 15 kilopascal and surroundings at 20 degree centigrade, find the actual work and reversible work between the inlet and the exit. So, this is a very classical situation related to analysis of steam turbine. I will first draw a schematic of the situation in the board. So, there is a steam turbine, it has an inlet state I and the exit state E. The inlet state is 6 MPa 800 degree centigrade. So, if you draw this in a TS diagram, sometimes there is a temptation of drawing it in a enthalpy entropy diagram, HS diagram. The reason is that for first law based calculations you require enthalpy, you do not really require temperature. So, if there is a diagram that directly gives enthalpy versus entropy, then that is very convenient. That in industrial application perspective is also known as Mollier chart or Mollier diagram. Here we are more concerned about the fundamentals of thermodynamics. So, we will not get into the use of Mollier chart, but we will I am just telling that as a passing note, because you may be requiring the HS chart for solving problems when you are participating in more applied thermodynamics courses. This is a fundamental thermodynamics course. So, you have the liquid vapor dome, the turbine is grossly specified by the following. So, in one you have a pressure that at which the steam enters the turbine, this is say given by Pi, and the pressure at which the steam exits from the turbine. Now, by isentropic efficiency we want to compare the actual work done by the turbine vis-a-vis the reversible adiabatic work, that is, if the state E would have been such that from I to E it would have been a reversible adiabatic process or an isentropic process, then what would be the work. So, if it would have been a reversible adiabatic process, let us call this as ES. This is not the actual state E, but this is the reversible adiabatic hypothetical state E. So, ES. The actual process will take the point E somewhere here. Now, the question is, where is the guarantee that this point E will be in the right side of ES, or it could also be in the left side of ES? Okay. So, let us look into that more carefully. So, between I to ES there is no, so you can decompose the change of state from I to E as from I to ES and then from ES to E. Just break it into two parts. From I to ES there is no change in entropy because it is a reversible adiabatic process. From ES to E you can write SE minus SES is equal to some Q by T plus entropy generation, right. This is what you can write. So, the question is that this is always positive, right. This could be plus, minus or 0. So, the net effect could be that this one is plus, when it is trivially plus, it is trivially plus, that this is the case when the turbine is adiabatic, because if the turbine is adiabatic this is 0, then entropy generation is always positive. So, E goes to the right side. This is what most commonly happens in industrial practice, because for all practical purposes the turbine can be treated adiabatic in most of the circumstances. However, there is no guarantee to that. You could have this Q plus, minus or 0. So, the net SE minus SES could be plus, minus or 0. So, technically this E could be in the right of ES, it could even coincide with ES and it could be in the left of ES, that must be conceptually understood. So, the very fact that we have in most of the practical cases E to the right side of ES should not develop a prejudice in our mind that E will always be in the right of ES. It depends on the nature of heat transfer across the turbine, that is what it is governed by, because other than heat transfer the entropy generation part, that is trivially positive part. Okay. So, now coming back to this problem, let us see what is defined, what is given. State E is 15 kPa, which is same as state ES, there is no difference in pressure between E and ES. So, this is 15 kPa. So, now if we apply the first law for per unit mass flow rate across the turbine, so you have Q plus HI. Say first law we apply for I to ES. In that case the reversible adiabatic Qs is 0 because it is adiabatic. So, I am completing the expression. So, I am writing this as Ws. Ws corresponds to reversible adiabatic per unit work or isentropic work. So, isentropic work will necessarily be Hi minus HES, this is HES. So, how do you know what is the state ES? Very simple. The state ES can be defined by two properties. One is SES is equal to SI, and SI is known from steam table. At this data you find out what is SI, and PES is equal to what? PES equal to 15 kPa PE. Okay. So, SES is equal to SI and PES equal to 15 kPa. This will give you what is state ES. It will be in the two phase region typically. So, you can find out the quality by setting SES is equal to 1 minus XES into SFS plus XES into SGS, where SF and SG are SF and SG at 15 kPa. Okay. So, once you calculate this what is ACS, then you can calculate what is HES also by using this interpolation formula for enthalpy. So, HES is equal to 1 minus XES into HFS plus XES into SGS. Okay. So, to summarize, by this calculation you know what is reversible adiabatic work. What is the actual work? For actual work you have to use the first law between the states I to E. Now, this turbine is a special turbine where heat transfer is not neglected. So, Q is there plus HI is equal to HE plus W, right. This Q is given, this Q is, it has a heat loss of 49.7 kilojoule per kg. Okay. So, this will tell you, and what is the exit state? The exit state is governed by what is the actual work. Now, you know that the actual work by the isentropic or reversible adiabatic work, this is defined as the isentropic efficiency. This is the definition, please make a note of this. I will talk about the definition of isentropic efficiency of a work absorbing device also after I complete this problem. This is the definition of isentropic efficiency of a work producing device, where the actual work is less than the reversible adiabatic work. So, then because you know what is Ws by substituting in this formula, and isentropic efficiency is given as 90%. So, from this you know what is W, you substitute that W here. Once you substitute that W here, you get what is He. So, what is asked is what is the reversible work between the inlet and the exit. So, to understand what is the reversible work between the inlet and the exit, you need to also know the entropy of the exit, not just enthalpy. So, you have to specify state E. How is state E specified? It is specified by PE and HE. Okay. So, from here you can get what is SE from table. So, what is the reversible work? HI minus T0 SI minus HE minus T0 SE. Okay. This is the expression that we have derived. This is a reversible work per unit mass because of change in state from I to E. So, if you know these values, T0 is given, T0 is 20 degree centigrade, that is 293.15 Kelvin. So, this will be 1636.8 kilojoule per kg. I just want to make a final note before concluding the solution of this problem. The final note is that this definition of isentropic efficiency is true for a work producing device only. For a work absorbing device like a compressor, the reversible adiabatic work is the minimum work, not the maximum. So, for isentropic efficiency of compressor, it will be the reversible adiabatic work input in the top in the numerator divided by the actual work input, which I mean both are in terms of magnitude at the bottom. So, for compressor, let me spell it out. Mod of work input by mod of reversible adiabatic work input. The spirit of reversing the expression is that efficiency we always have an imagination, it cannot be more than 100%, but it is always a comparison between reversible adiabatic with the actual case. Which one will be there at the numerator and denominator depends on which one is more and which one is less. Okay. So, let us solve another problem. Problem 8.3. So, problem 8.3, a 2 kg piece of iron is heated from room temperature 25 degree centigrade to 400 degree centigrade by a heat source at 600 degree centigrade. What is the irreversibility in the process? So, this is a very straightforward typical problem, but let us work it out. So, you have a mass of 2 kg of iron, your T1 is 273.15 plus 25 Kelvin, T2 is 273.15 plus 25 Kelvin, and the temperature of the ambient is 273.15 plus 600 Kelvin. So, for knowing the irreversibility, you need to know what is the entropy generation. To know the entropy generation, you have to know what is the heat transfer. To know the heat transfer, you have to apply the first law. So, we start with the first law for the copper block or iron block. Q12 is equal to U2 minus U1 plus W12. Copper block does not do any work. So, the heat transfer is simply, and U2 minus U1 for a solid object like copper is mc into T2 minus T1. The specific heat of copper C is 0.42 kilojoule per kg Kelvin. This data is required for solving your problem. So, you get what is Q12. Then you apply the second law, S2 minus S1 is equal to Q12 by T0 plus entropy generation. Okay. So, in this case we have to clearly see whether so this is, here we have to make a decision. What is the decision? The decision is that is this the ambient temperature or this a heat source temperature different from the ambient temperature, right. So, here it appears that it is not ambient temperature, it is the heat source temperature at 600 degree centigrade. So, the irreversibility that you calculate, the reference temperature is always important. You could calculate irreversibility by taking the heat source as the reference temperature, but that is called as immediate surrounding. Normal tradition is to calculate irreversibility with respect to the actual ambient temperature as the reference temperature. So, if we do not choose this to be the ambient temperature, it is not clear in this problem statement that this is not the ambient temperature. So, in that case the heat transfer is taking place with this thermal reservoir and not T0, right. So, the entropy generation, this will appear in the heat transfer term, and S2 minus S1 is mc ln T2 by T1. So, this in this expression everything is known except entropy generation, which is found out. The irreversibility is simply T0 into entropy generation. Here you have to make a decision that what is this T0, right. Normally this is called as Exergy reference temperature, which is the ambient temperature. So, in this problem the intuition is that the ambient temperature is 25 degree centigrade and not the 600 degree centigrade, right. So, then if you put that as T0, so this will give you the irreversibility, and the irreversibility in this case is 96.4 kilojoule. Okay. So, let us stop here for the time being. We will continue with more problem solving in the next lecture.